Let's look at types of nuclear radiation that are produced. Types of nuclear radiation are the types of radiation that are emitted during nuclear reactions, during radioactive decay. So alpha particles are helium nuclei. They're very large particles, relatively speaking, and they have a large charge. They're +2. Because they're charged, they can easily ionize other particles. They are slow-moving. They're large, slow-moving, and ionize other particles easily because they're so highly charged, +2. If I wanted to stop alpha particles, alpha radiation, paper would do it. Cloth would do it. In fact, the dead layer of skin on the surface of your skin will protect you against most alpha radiation. Beta particles, again, are electrons that are generated by the nucleus. They're very tiny compared to alpha particles. They're relatively fast-moving. Certainly fast compared to alpha particles. They have a -1 charge, so they can ionize particles, but not as much as alpha particles. To stop beta particles, what I would need is a thick layer of glass or a several centimeter thick layer of metal. A couple inches of wood would probably do it as well. The third type of radiation is gamma radiation. Gamma radiation is not particulate, it's pure energy. Electromagnetic energy is what the EM stands for. It has no charge because it's pure energy. Because it's such high energy, it causes other particles that it comes in contact with to become ionized. The energy is so high it just knocks the electrons out of those neutral atoms. Gamma radiation moves very quickly. Because it's electromagnetic radiation, it moves at the speed of all electromagnetic radiation. That speed is 3.0 times 10 to the 8th meters per second in a vacuum and also in air. If we wanted to stop gamma radiation, we would need several inches of lead. If we didn't have lead, we would need several feet of steel and concrete. Now, for comparison of these three types of radiation, one way you can think about these is just in terms of destructive tools. For example, you could think about an alpha particle as a cannonball. It's pretty big, doesn't move that fast, and it does some serious damage, but locally, and only whatever it hits. If it doesn't hit, it's not going to do any damage. Beta particles, more like a bullet. It travels much more quickly. It has a smaller region that will create damage, but it creates damage through a much thicker layer of the material, the organic item that it might be hitting. Gamma radiation, you could probably think of in terms of a laser. It travels very fast, it's very high energy, and so it can just, rather than going through something, it can act as a high-powered knife and just cut off chunks of a living organism. Binding energy of the nuclei is essentially the energy that holds the nuclear particles together. And if you stop to think about what a nucleus is for any length of time, you might have wondered what holds it together, because we have all this positive charge in the form of protons, and normally, if you know anything about electrostatic charge, like charge repels. So all these positive protons are repelling each other. They don't want to be next to each other. Neutrons are neutral. They have no charge, so they can act as a distance buffer, but they're not going to do much to help override that repelling charge that all the protons have for each other. So this energy holds these protons and neutrons together is, in fact, the weak and strong nuclear forces are the four main types of force that exist as we know it. So for an isotope, the larger binding energy it has, the more stable its nucleus is. And we can figure out what this binding energy is by comparing what an idealistic isotope mass would be compared to finding that isotope in nature and determining its mass. For example, if we wanted to take a look at building an oxygen-16 isotope, it's made of 8 protons plus 8 neutrons plus 8 electrons. So if we were to take the mass of protons, multiply it by 8, mass of neutrons, multiply it by 8, mass of electrons, multiply that by 8, add them all up, what we would find is we have a mass of 16.131923 AMUs, or atomic mass units. When we're dealing with atomic masses of isotopes, we tend to go out to 5 or 6 decimal places. If we go out in nature and collect a bunch of oxygen-16 isotopes, however, and mass enough of them to get a measurable quantity, what we find is the mass of these isotopes is not what we predicted it would be, it's less. Actual mass of oxygen-16 isotopes is 15.994915 atomic mass units. If we take the difference between these two numbers, what we get is something called the mass defect. So for the oxygen-16 isotope, the mass defect is 0.137008 atomic mass units. So what happens to the mass? Where did it go? Turns out this mass is converted into energy. And this is the energy that holds these nuclear particles together. We have Einstein to thank for the equation for relating the amount of mass lost to the amount of energy generated by this conversion from mass to energy. So M is the mass defect, but we need to convert it to kilograms. So on your green sheet there is in fact a conversion from AMUs to kilograms. It's 1.66 times 10 to the negative 27 kilograms per AMU. So the mass defect we find is 2.274 times 10 to the negative 28 kilograms. Now we can use this mass. C is the symbol for the electromagnetic speed, 3.0 times 10 to the 8th meters per second. And we can calculate the amount of energy generated by this conversion from mass to energy by following through with Einstein's equation. What we find is we get 2.0446 times 10 to the negative 11 joules. And this is the amount of energy per nucleus. So it's joules per nucleus. And this is the binding energy per nucleus. Well, it's all very interesting, but what actually is more useful is to find out what is the bonding energy per nucleon. Nucleon is simply a nuclear particle. It can be either a proton or a neutron. So to find the binding energy per nucleon, I'm going to take the binding energy per nucleus and I'm going to divide it by the number of nucleons. For our oxygen isotope, we have 16 nucleons. So if I do the math, what I will find is that I have 1.2779 times 10 to the negative 12 joules per nucleon. And binding energy per nucleon is a measure of how stable an isotope is. It turns out that iron, and in particular iron 56, is the most stable isotope in the universe. This graph shows its binding energy, and it's in mega electron volts, which is just a different way of representing energy, compared to the mass number. Fusion is what generates isotopes, and I keep trying to make them more and more stable to increase the binding energy per nucleon until I reach iron. When I have very unstable isotopes, the very large ones, they are going to go through fission to try and reduce the isotope size and isotope mass, the goal eventually being to try and get to something more stable, the ultimate goal being to try and reach this iron 56 isotope. That would perhaps be the reason why our world is made primarily of iron. If you think about the core, the mantle of the earth, they are mostly iron. Iron meteorites are flying throughout the universe, and those are the type that periodically also reach Earth and was our first source of usable iron, at least on this planet.